The last video showing the solutions for our practice test. We're going to be looking at material from linear inequalities, and also we'll be looking at some quadratic or parabola stuff in a second. Okay, so first thing we're asked to do here for question 10 is we're asked to show whether the points represent solutions to the inequality 5x take away 6y less than negative 12. And we're asked to do this both with a graph and algebraically. Okay. We're also provided a graph with which to do this. So I'm actually going to rewrite this equation out here because I know that if I want to answer if these points are solutions graphically, I'm going to need to graph this inequality. Now, there's a few ways to do that, but I think the best and most clear way for me is to put it into slope-intercept form. So I want it in something like y equals mx plus b form, so I know the slope, and I know the y-intercept. There won't actually be an equal sign here, though. There will be a greater than or a less than sign in its place. So we'll cross that bridge when we come to it. Okay, so to put things into slope-intercept form, I need to isolate y. Okay, so I need to get everything away from this side of the inequality that isn't y. So it means I got to get rid of this negative 6, and I got to get rid of this 5x. So the dinner plate rule says I usually start with the thing further away from my variable I want to isolate, furthest away from y, which in this case is 5x. So I'm going to get rid of my 5x first. To do that, I'm going to take away 5x. And what I do to one side, I got to do to the other. So 5x take away 5x leaves us with 0 there. And it leaves us with just a negative 6y on the left-hand side. And that's less than negative 5x take away 12. All right. Almost done, so now I got to get rid of this negative 6, which is being multiplied by y. So the opposite of multiplying by negative 6 is dividing by negative 6. So I got to divide every term by negative 6, like so, and that cancels these guys out. However, I'm left with a y here. There is a rule about inequalities. If I divide by a negative, or if I multiply by a negative, I actually have to flip the direction of this inequality. So rather than saying less than, I have to change it to a greater than sign. So we want to watch out for that. Negative 5 over negative 6, well, that simplifies to positive 5 over 6, x. Negative 12 divided by negative 6, that's positive 2. Okay. So I can graph that. I can say, okay, well, I know a few things about this line. I know the slope is 5 over 6, meaning it rises 5 and runs 6, but the y-intercept is at 2. That means the intercept is at 0, 2. So to graph this, I'll start with my y-intercept as 0, 2. And I'm going to rise 5, 1, 2, 3, 4, 5, and run 6, 1, 2, 3, 4, 5, 6. And I could keep doing that if I wanted to. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5, 6. So it's a little bit off the graph, but we can confirm that generally speaking, these are points on the line. Now, however, we want to make sure we see that if this is a greater than sign, rather than a greater than or equal to sign, we want to make sure we use a dashed line to represent this inequality. I'm just going to grab a ruler. Highlighter. Alright, and so I'll connect these dots. So this last dot is a little bit off because I kind of freehanded the last few steps, but I'll make sure I line up these steps here. Okay. I'm not, of course, done. I need to shade in a particular region. Now this says the y values are bigger than the line 5, 6x plus 2. So actually that means we're going to be shading the region above this section. So I can go ahead and shade in this region like so. Not too much shading. I want to be able to read anything else that I need to put in this region. But something like that. Now there's a nice line. Okay, so the next thing I can do is I can also determine if, so first of all, I can take a look at these points. 0, 2. 0, 2. Okay, that's a point right on the line. Now, however, this dashed line means the points that are on the line are not solutions. So this actually means that 0, 2 is not a solution. So that's the point 0, 2. So maybe I'll make a note. That's point 0, 2. And I'll put a little x to indicate that is not a solution. I'll grab the point 5, 5 next. So 5 in x, 5 in y. So 5, 5 is also not a solution because it is not in this area that represents solutions to this equation. It does not give us truth. And we're going to see what we mean when we say it doesn't give us truth in a second. And lastly, we look at the point 2, 4, which means 2 in the x direction and 4 in the y direction. And the point 2, 4 is a solution. It is in the region that represents possible solutions. So let's take a look at what we mean when we say that. So we're also going to confirm this algebraically. All right, so if we have a point x and y, what it means to be a solution means it tells you that it gives some sort of situation where it tells us an algebraic truth, which means we get something like a statement that says the left-hand side is somehow, it's going to be less than the right-hand side in this case, because we have a less than sign. So what we're going to do is we're going to put in our values for x and y, and if this gives us truth, then the point is a solution. So let's take a look at what we mean by algebraic truth. All right, so my original line is 5x take away 6y is less than negative 12. And if my x value is 0, so I can write 5 times 0, take away 6 times my y value is 2, and maybe that's less than negative 12, so we're going to find out. 5 times 0, that's 0. Take away 6 times 2, so that's 12. Is that less than negative 12? Is a negative 12 less than negative 12? No. This is false. Therefore, the point 0, 2 was not a solution. It did not give us truth. We were really concerned about truth. All right, moving on. So let's take a look at the point 5, 5. Okay, so I'll put in 5 for x. 5 minus 6 times 5 for y, and that's less than negative 12 again, so that means 5 5s is 25. Take away 6 5s is 30. Is that less than 12? Pardon me, less than negative 12? 25 take away 30, that's negative 5. Is that less than negative 12? And the answer is no. You'd rather have negative $5 than negative $12 because negative $5 is more. It's kind of weird to think about negatives being bigger or smaller, but I'd invite you to look at the number line if you're needing more convincing about that. This is also false. So therefore, 0.55 was not a solution. Okay. Lastly, we'll look at the point 2, 4. All right, so that means x value is 2, y value is 4. Great. All right, so that means we've got 5 times x is 2, take away 6 times 4, and that has to be less than negative 12. So let's take a look at that. 5 2s that's 10. Take away 6 4s is 24. Is that less than 12? Pardon me, negative 12. 10 take away 24. If I start at 10 and I go 24 in the negative direction, that gets us to negative 14. Is that less than negative 12? Yeah, it is. Negative 14 is less. This is true. Therefore, 2, 4 is a solution. All right. So far, so good. I need to grab a power cord. And so the key idea here is we have two different ways of demonstrating whether something's a solution. We have a algebraic argument for whether a pair of values gives us a true statement or a false statement, just by replacing the variables with specific numbers. And then we can find if we get falsehood or true. We also have a graph that visualizes that information. We have these 3 points. And either they're in the shaded region, meaning the very great region that holds truth or solutions for us, or we have this section that is not shaded, meaning those values are not solutions, and we also have the points that are on the line, which in this case represent things that are not solutions, but a solid line would indicate that they are solutions. Okay, that means I could take any of the points that are in this white region here, and like for example the point 8, 2, and I could expect there would not be a solution. It would give me something false, like -5 is less than -12. Great, moving on. Okay, we'll go to question 11. Give the system of inequalities that describes the following diagram. In other words, write the equations, or inequalities is the word we use if we're not using equal signs, rather for shading a region, that match these lines. Okay, so I'm going to choose one at random. I'm going to choose the top one here. I guess it's the top on the left, but it turns out to be the bottom one on the right. So if I need to give the equation of this line, I would start by trying to find the y-intercept. Y-intercept is -1, so that means B is at -1. And then I would try and find the slope. I would say, okay, well, it looks like I rise 1, I run 2, but just to make sure, I do it again, rise 1, and I would run 2. So it looks like the slope has a rise of 1 and a run of 2. Rise over run is a slope of 1/2. And okay, and it looks like we're talking about shading the region below that line. So that means we're looking at y values that are less than that line. Okay, so I'm going to write that down. So it looks like in mx plus b form, we could say that y is, I'll get to the symbol in a second, but I could say it's 1/2 x, take away 1, mx plus b. And I know that because I have a solid line, the values that are on the line are also solutions to this line. And we're looking at values less than that region, so it's going to be y values are less than or equal to 1/2 of x, take away 1. And we're going to do the same thing with this second line. This is a dashed line, I noticed, so that's going to be slightly different. So for this one, let's start with the y-intercept. Looks like the y-intercept here is -4. And the slope looks like it rises 2 and runs 1. Rises 2 and runs 1, 2 and 1. So it rises 2 over 1, which simplifies to 2. Okay, so to express that one, it looks like we'll just say that y is, again, we'll come back to that symbol, but the slope is 2x, and the y-intercept is -4. And if I look at this dashed line, it looks like we're shading the regions above that value, so it looks, or that line, so it looks like we're going to be looking at y values that are bigger than or above the line itself. And it's a dashed line, meaning we're not going to be accepting values as solutions that are actually on the line, only the ones that are above it. Great, and that's it. That's all we have to do for a question like that. Okay, moving on. So the next question looks like it's got a lot of moving parts. So we've got a reading sample here that describes our situation. and it continues over on this page. So we're going to start with a highlighter, and we're just going to go slowly and read our reading sample until we feel like we really understand what it means. Okay, so what do we have here? Dorothy is ordering some art supplies. New oil paint costs, that should be an S, $6 each. So oil paint costs $6 each. And watercolor paints cost $8 each. So that sounds important too. Watercolor paints cost $8 each. All right, and she needs to make sure her bill comes to no more than $96. So no more than, okay, I'm already starting to think about an inequality there. $96. So that already gets me thinking about maybe defining some variables, x and y maybe, and I can almost think about making an equation there, but let's just make sure we read the rest of this sample. Maybe there's other things going on. Okay, so what do we have here? Dorothy needs at least 4 different oil colors for our final art project. So she needs at least 4 different oils. And she needs at least 6 different watercolors for a project she's working on for a portfolio. Okay, so she needs at least 6 different watercolors. Okay. And lastly, the question asks, how many different types of each paint could she buy? So maybe we're in the habit of maybe using a different color. How many different types of each paint could she buy? So that's the big question. All right. So first thing we're asked to do is make a let statement to define any variables for this problem. Okay. So maybe we should say we'll let, we've been using x and y, so let's let x, and that's going to represent, what's variable? What do we not know? Well, it looks like we don't know how many, or the number, of different types of paint. But we don't want to let x just represent different types of paint, or numbers of different types of paint. That's going to be multiple values. So we want to go back and we'll say, okay, well, specifically we're talking about oils and we're talking about watercolors. So maybe to make this more straightforward, we should say, let's let x represent the number of oil paints Dorothy is ordered. We're going to let x represent the number of oil paints. And I guess there's another unknown, which is the number of watercolors. So we'll let y represent the number of watercolors. Great. I apologize for my horrendous handwriting. All right, moving on. So what do we got here? So we're also asked to make a system meaning multiple inequalities, to represent the situation. Okay. So this takes a bit of practice to get right, but you guys have lots of practice with this by now. So let's take a look. Okay, so let's start maybe first with an assessment about the amount of money things will cost. We'll start there. So we know it's her total can't come to more than 96, which is another way of saying it must be less than $96, or maybe less than or equal to $96. And her bill is going to be composed of the amount of money she spends on oils, the amount of money she spends on watercolor. Okay, so let's start there. I find sometimes it's helpful for me to write out the sentence before I turn it into math. So maybe I'll say the cost of oils plus the cost of, I'm going to abbreviate it to WC, watercolors. And that's got to be less than, but it could be equal to her, what do we call it, her budget for paints. All right. And then we need to figure out a way to represent the cost of oils. So in total, we know that she's going to buy X oil paints. And we know that oil paints cost $6 each. So the cost of Dorothy's oils is going to be $6 for every X oil paints that she buys. So 6X. And we're going to add that to the cost of the watercolors, which watercolors were $8 each. So we're going to represent that as $8 for every Y watercolors. So 8Y. And that's got to be less than or equal to the total amount she had to spend, which was $96. I'm going to write that a little bit more condensed. 6X plus 8Y is less than or equal to 96. A very deal-with-able equation. All right. I'm going to put a little line down here so I don't get confused when I go back to read this later. Maybe I'll put a box around this as well. So that's one of the linear inequalities we're going to deal with, but we're asked to make a system. The word system implies we're going to have multiple lines or inequalities all in the same, all describing the same situation. So let's go back and see if there's any other details we need to see if we can make an equation for. So here we see that Dorothy needs at least 4 oils. At least 4 oils. So no matter what her budget is, she's got to have at least 4 oil paints. Okay, so if X represents the number of oils, we can say, so the number of oils must be at least, meaning greater than or equal to, could equal 4. Number of oils is greater than or equal to 4. And we have a variable to represent the number of oils, so instead of writing a sentence, I can write that as a number and variable sentence. X is greater than or equal to 4. And also, we have another stipulation. The number of watercolors must be at least or greater than or equal to 6. That means Y is greater than or equal to 6. And it looks like now we have represented all of the key ideas represented in this problem so far. Okay. So now we will label our axes. So X represents this axis here, so that's our X-axis. And it represents the number of oil paints that Dorothy buys. Okay, so this represents the number of oil paints. All right, and the y-axis, that represents the number of watercolors. So that's the number of, I'm just going to abbreviate that, WC for watercolors. Okay. So that's the first thing. We're asked to label our axis and then graph the system. Okay, so let's start with this guy here. Okay, so if I want to graph that, I need to put it in slope-intercept form. So I'm going to isolate y. So I'm going to rewrite that over here, first of all, before I do any math steps. Then I'm going to get rid of this 8 and the 6x, but I'm going to get rid of the 6x first, a little further away. So I'm going to take away a 6x. Take away 6x. They cancel out. And I get 8y is less than or equal to negative 6x plus that 96 left over. Almost there. I got to get rid of that 8, so I'm going to divide by 8. Divide by 8. Divide by 8. Cancels. And y is less than or equal to negative, these guys are both even, so I can divide them both by 2. So that's what I'm going to do. I'm going to say negative 6 divided by 2 is 3. 8 divided by 4 is, 8 divided by 2 is 4. X plus 96 over 8. I know that from my 12 times tables. I know 8 twelves is 96. So that gives me the inequality that is graphable. It's the same inequality, describes the same truth, assuming I didn't make any mistakes. And that means I can graph that. So I can say, okay, my y-intercept is 12. And my slope is, looks like I'm going to rise negative 3 and run 4. I'm going to rise negative 3 and run 4. And I can do that along the entire graph. Negative 3, run 4. Negative 3 and run 4. And this is a less than or equal to graph, meaning we're going to be looking at a solid line. Values that are on this line represent solutions to that problem. So what that means in terms of paints is that if Dorothy buys some combination of oils, X, and some combination of watercolors, Y, and they happen to add up to exactly $96, that's actually going to be okay. That's something that is allowed to happen. She just can't go over $96. All right, and we say, well, we're looking at the Y values less than or equal to that line. So we're going to be graphing, or rather coloring in, the regions below. I'm going to grab, now it's pretty easy to make this look like a jumbled mess with a pen. So what I'm going to do is I'm just going to grab a few pencil crayons. So I'm going to use my cool gray color to shade underneath this line. I think the color scheme I've chosen randomly is going to be a little ugly. We'll have to deal with it. So we're shading just the region underneath. That means any of these points in this region represent possible combinations of oils and watercolors that will keep Dorothy under budget. And the values that are on the line will take Dorothy to exactly $96 worth of spending. And any of those are fair game at this point, because what we've only graphed is the first stipulation about her budget. We have not included these other stipulations about Dorothy needing to have at least 4 oils or 6 watercolors. We'll deal with that in a second. Okay. So on to the next one. Next one, the number of oils has to be greater than or equal to 4. Okay, so if I graph a line like x is equal to 4, that's going to be a vertical line that intersects the graph at 4. And what that line really means is we're looking at all the values where x is 4. And it doesn't matter what y is. That's why y is not in the equation. Just x is 4. So no matter what y is, x is 4. And it's in the less greater than or equal to sign, meaning I can draw a solid line to represent that, not a dashed line. Okay, that's the line. So it doesn't really show up that strongly, so I'm going to need to make that a little bit more deep and obvious there. So let's do something like that. There. Still a little light. It looks almost as, doesn't really look that much darker than the axis. I'm going to make this one a little darker as well, to really emphasize. And I hope that when I color this in, it's also going to make it a little bit more obvious what region I'm talking about. So, okay, that is my line x is equal to 4, but I want the line x is, or pardon me, the inequality line is greater than or equal to 4, so I'm going to shade the regions of x that are greater than 4. And we all know how well gray and pink go together. And here we're seeing this overlapped region. So the meaning of that overlapped region is that's a region in which Dorothy is going to stay under budget and also by more than 4 watercolors. That's what that region represents. The region over here says she's going to stay in budget, but she won't have enough watercolors, or pardon me, oils. She'll have enough oils. I said watercolors. That's confusing. We'll get to the watercolors in a second. Okay. And I feel like maybe at this stage I need to shade, that makes me think my cool gray needs to be shaded a little bit more strongly to emphasize that that's a region of overlap. So I'm going to shade a little bit more strongly there. Okay. And lastly, we need a value of watercolors greater than or equal to 6. Okay. And so that means I'm going to be looking at a line like y equals 6. And we'll look at the values bigger than it, bigger than 6. So my experience from the last line told me I need to draw a really thick line here. Not bad. Okay, a little better. The last one. And I need to shade a region above that one. Now this isn't going to scan very nicely, I realize. However, hopefully if you're watching this, you can see what we're doing here. And eventually we're going to have this region shaded in with green. And you can see this little triangle in the middle is an overlap of all three of these regions. So that means not only is Dorothy going to be under budget and spend less than $96, but she's also going to have at least 4 oil colors and at least 6 watercolors. Okay. Great. So this is our solution set in here. Maybe I'll shade that in even darker. Those are our solutions. All the possible combinations of oils and watercolors are going to keep Dorothy under budget, and she'll have enough watercolors for her portfolio and enough oils for some art project. So that means she could have, say, 5 oils and 7 watercolors, or 4 oils and 7 watercolors, or 6 oils and 6 watercolors, or 8 oils and 6 watercolors. Any of these are options for her. All right. So the corners of the solution set are this one here. So that's the point 4, 6. That means 4 oils and 6 watercolors. The point here, which is 8, 6. 8 oils and 6 watercolors. And the point here, 4, 9, which means 4 oils and 9 watercolors. These are all possible optimal solutions. Oh, I didn't need to write that here. These are our optimal solutions, meaning if we add some other stipulation about, say, weight, which we'll get to right now, one of these is going to represent our best option. Now let's take a look at that right now. All right, looks like we're told a little bit more detail about this question. We're told Dorothy is delivering her paints by mail and charges by weight. So oils weigh 5 ounces each. Okay, and watercolors weigh 8 ounces each. Watercolors weigh 8 ounces each. What is the lightest? What is the lightest that Dorothy's purchase could be? What's the lightest that Dorothy's purchase could be? So we want a combination of points that is going to give us the lightest package. So I'm going to test these values and see if we can figure out the solution that gives us the lightest package. All right, so I'll test this one first, the point at 4, 6. So that means 4, 6, or 4 oils and 6 watercolors. So 4 times 5 ounces plus 6 times 8 ounces. And that's going to weigh 20 plus 6 times 8 is 48. So 68 ounces. Okay, so that's one possible package that Dorothy can purchase. Okay, so moving on. So let's take a look at the point 8, 6. 8, 6 is 8 oils, so 8 times 5 ounces for each of those oils, plus there's 6 watercolors, and each of them weigh 8 ounces each. I guess it's a tube. All right, and 8 fives, that's 40, plus, I already know this one, that's 48. It means we're talking about 88 ounces. Okay, and lastly, we'll test this last one for 9, 4 oils and 9 watercolors. So that means 4 times 5 ounces plus 9 times 8 ounces. So that's 20 plus 72, or 92 ounces. Okay, so it looks like the lightest package that Dorothy could purchase is 68 ounces. So we can answer that here. If we're asked a word problem, it's nice to answer in words. The lightest purchase is 68 ounces. And I might even add a little bit more detail. That's from 4 oils and 6 watercolors. All right. So let's move on now. That's everything we're going to need to do for our rates question. So let's move on to quadratics. All right. So first, we're asked to identify the vertex of the following parabola. So we know that a parabola follows this general h squared plus k formula, where these two values tell us where the parabola changes direction. That's always the point hk, no matter what. So, for example, I could take a look at the parabola in question A, and I know that there's our a value is -4. Our h value, the number taken away from x, that must be a -7. We took away -7. That's why we got a +7 in here. So that means that our h is -7. And our k value, the number added on to the end, doesn't really show up in the equation, which means we're really adding 0. Okay, so this parabola has a vertex at -7, 0. It's been moved 7 to the left and 0 up and down. Now, I know that some people have also memorized that you flip this inside term. So if it says +7, you just write it as -7, and you just write the number added out to the right as it is. That's fine. All right. How about this one? Our value of a, that's 2. Our value of h in this case, well, we can imagine if we wrote an equation such as y equals 2x minus 0 squared plus whatever, some number. That x minus 0, well, if you take 0 away from anything, that doesn't really change it, it just becomes x. So another way to write that would be y equals 2x squared. And I don't really need these brackets anymore for this squared, it just applies directly to the x. So I could actually say it's 2x squared plus whatever. So what I'm trying to say here is it doesn't look like we've been moving left or right any units, and so actually our h is 0. And this number on the outside, that's our k value, that's how much we've moved up. So that's k is 8.5. Okay, and so we have a vertex then at 0 and 8.5. All right, so go a little bit more quickly through these guys, or maybe a little bit more straightforward. So we've got a vertex here, pi. Pi is just a number, nothing special about it. It's the number 3.14159.265 and so on, but it's just a number. So that means I moved pi units to the right and 4 units downward, -4. Simple as that. And if I don't know specific values, well, it doesn't matter. I've still moved n values, whatever n takes the value of in this case, to the right, and p units up. They're not, so I can choose a value for n, put it in, and then I move that many units to the right, and so on. Straight up, okay. All right, now this is not one that I can solve or show you. Actually, you know what? I probably can. Now let me just try that. So I did this earlier because I thought I would just need to write the equation down, but I can show you at least what I've done. So I went to this page. Oh, right. Okay, hang on a second. That's what we call positive feedback, so I gotta make sure that I'm not showing you what I'm recording. Otherwise we get some interesting physical problems. So we'll minimize that so none of that shows up. All right, and so this is what I worked out. So I made a parabola. Your mileage may vary. You may have put the vertex in a slightly different place, but I made this equation here, y equals -0.08 was the a value I ended up getting. I found my vertex was at 6.5 and 7.5. Now, you may have found slightly different values, and there's not just one parabola that models that. However, there's probably a best parabola that models that. So I'm going to write that down here. So y equals negative 0.08 and x minus 6.5 squared, and we add